Hello, my name is Josh Urban Davis from Dartmouth, and today I'll be presenting IllumiWear, a fiber optic-based e-textile for multimedia interactions. The history of textiles is closely intertwined with the history of computation. This is extremely evident in the development of the Jacquardi loom around 1803, which used punch cards in order to indicate to the weaver the next step in the textile manufacturing process. By mechanizing the procedure for textile production, Jacquardi's loom allowed for quicker and more complicated fabrics to be created. This use of punch card as a systematized direction system later became the inspiration for punch card computation. This notion was not lost among later computer scientists. Mark Weiser's ubiquitous computing revolution, for example, stated that the most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they are indistinguishable from it. Technologists who went on to develop e-textiles took this declaration quite literally. Electronic fabrics, as opposed to traditional wearable electronics, are deformable and conformable, providing affordances not available to traditional rigid electronics. In this way, e-textiles present the potential to be truly ubiquitous computing platforms in that fabrics are omnipresent in our environment and are capable of deforming into a variety of shapes. Within the instrument building community, many examples exist documenting the effectiveness of fabrics as deformable instruments, including the work of Donu, Wikasano's fabric keyboard, and the many, many descendants of the data glove. Inspired by this rich tradition, today we present IllumiWear, a prototype light-sensing fabric as a music and visual input device. IllumiWear is composed entirely of fiber optics woven like a traditional tapestry or basket. This allows IllumiWear to maximize the visual potential output of fiber optics while maintaining the tangible pliability of previous deformable instruments. IllumiWear is fully reprogrammable according to an artist's practice and is meant to serve as an open platform for artists and designers. While our device is built on a tradition of music input devices, we offer a series of contributions over previous work. These include descriptions of IllumiWear's hardware implementation and prototype design, which is cost-effective, development of a light-sensing technique for fiber optic woven e-textiles, and a technical evaluation of the micro-bending touch, macro-bending touch, and locality of touch deformation recovery on our prototype e-textile. We provide instructions for hardware reproduction, as well as a design schema for extending the capabilities of our e-textile to a deformable instrument. Fiber optics are cables composed of a refracted medium such as glass or plastic, capable of propagating light across long distances. This light, once propagated, can be parsed for information. The IllumiWear fabric itself is composed of many such cables, separated into bundles and woven together in a plane weave, similar to a basket. This creates a fabric composed entirely of fiber optics, which can be equipped with sensing capabilities to serve as means of input, while not compromising the inherent visual properties of the cables themselves. To explore this concept of using light as a dual means of input and output, we designed and developed a prototype using off-the-shelf sensors and fiber optic cables. In order to ensure the feasibility of our design for as many potential users as possible, we focused several design decisions on ease of implementation and economical efficiency. Our design uses woven fiber optics with a light emitter positioned on one end of the cable and a light sensor positioned on the other. As the fiber optic cable bends, the amount of light registered by the receiver should also subsequently be affected by the cable deformation. By weaving these fiber optics together, we can create a fabric capable of extracting not only the severity of deformation, but also the location of the deformation. The weaving pattern used in baskets creates a grid-like lattice. Applying pressure to any element of this lattice would not only affect the light loss of the deformed fiber optic cable, but also the cable above and beneath the target cable. We leverage this property of fiber optics as an input mechanism to our fabric. Our design requires that propagated light be emitted from one end of each bundle and a light intensity sensor be equipped to the other end of the bundle. Our sensors, therefore, must be able to capture light intensity within a modest sampling frequency. To simplify our design, our photodiodes must have built-in transimpedance amplifiers. To serve this purpose, we chose the TI-OPT101J illustrated here. because it not only satisfies all the needs mentioned above, but is also sensitive enough to describe optic fiber micro and macro bending. The OPT-101 is a monolithic photodiode with on-chip transimpedance amplifier. The integrated combination of photodiode and transimpedance amplifier on a single chip eliminates many common design problems such as leakage, current errors, noise pickup, and gain peaking as a result of stray capacitance. Output voltage increases linearly with light intensity. The amplifier is designed for single or dual power supply operations. It also is quite cost-effective. As a mode of input, we focused on developing detection methods for 3 types of deformation: microbending, macrobending, and locality of deformation recovery. Microbending on fiber optics describes gentle touch input and is best utilized for discrete input gestures such as triggering a button. We found that a microbend induced between a 5 and 7 millivolt drop when the bend occurs. This indicates that even if the bend is slight, the system is able to capture it. The voltage drop depends on the amount of bending induced in the mesh or in the particular strand for which the sensor value drops. These variances will be addressed later in our future work section. Macrobends similarly describe large deformation gestures such as fiber bends 90 degrees or greater. We found that a macrobend induced between a 12 and 15 millivolt drop when the bend occurs, which is a significantly larger drop than microbend. This indicates that the system is able to distinguish between different levels and severities of bends on the mesh. Additionally, since the cables are woven on top of each other, intersection detection allows our sensor to recover the severity of bend as well as the location of deformation. The sensing values of 2 optic fibers drop simultaneously by approximately the same percentage. This indicates the 2D location of the bend. The variance between the 2 values is significantly different for some intersecting bundles, which is the result of varying number of fiber optics collected within each bundle. In future implementations of the system, ensuring consistent division of fiber optics between these bundles could be helpful for normalizing these results. We will address this further in our future work section. These basic gestural input capabilities of microbending, macrobending, and location recovery enable IllumiWear to express a wide variety of musical and visual ideas. Location recovery combined with microbending and macrobending differentiation allow IllumiWear to be used as a traditional keyboard with pressure sensitivity. Similarly, one-dimensional location recovery along a fiber bundle allows expressive sonic modulation. Since our sensing principle is sensitive to light emission variance, and since various emitted colors of light propagate different emission intensities, varying the color of light itself can produce varying sonic qualities. In this way, varying the color alone can directly modulate the sound. Additionally, an ability to distinguish between microbending and macrobending can be used to control modulation of sound via tangible interaction. This can range from a rolling or bending gestural modulation. To a complete, tangible deformation. This preliminary work presents many exciting opportunities for future work and investigation. One limitation is that the stiffness of the fabric, composed entirely of fiber optics, is not entirely as pliable as traditional fabrics. One solution is that if the artist desires a more pliable e-textile, fiber optic threads can be embedded in a more traditional, flexible fabric, such as spandex or cotton. As mentioned earlier, inconsistencies in fabric bundle size result in inconsistent baselines for light emission. There are two approaches we can take to addressing this problem. One, on the hardware end, is ensuring greater consistency in bundle size. However, if this becomes infeasible on the software end, a calibration phase could be used to normalize the bundles to a desired range. A sigmoid function, for example, could be used to confine all output values to a specific range between 0 and 1. Another limitation is that our fabric is incapable of distinguishing between concave and convex bends. This limits the amount of information that is able to be retrieved to purely symmetric deformations. A clever weaving technique could address this problem and allow for more information to be recovered from the mesh, such as asymmetric deformations. Incorporating previous work on fiber optics as visual displays could greater strengthen the potential visual output from the instrument. And while our technical evaluation demonstrated the instrument's ability to be used as an expressive device, it hasn't been extensively tested with various users. Future work in this domain would benefit greatly from an extensive user evaluation. For more information, please see our paper. If you have any questions, please feel free to email me or follow me on Twitter. Thank you for your time and attention. My name is Josh Urban Davis, and this has been IllumiWear.